now that we know how to multiply matrices together, we can take powers of matrices and other more complicated things. So for instance, if A is square, then A squared is well defined. It's just the product of A times itself. And since A is square, the length and the height of the matrices will line up, and that product will be well defined. And in general, we could talk about higher powers of a matrix as well. And this is just what you get by multiplying together some number of factors of that particular matrix. And so now we know how to take linear combinations and take powers. And so if we had some polynomial, like say f of x was x cubed minus 2x, then we could actually apply f to the matrix A, and we'd have a well-defined thing that we could talk about. It would be a cubed minus 2 times a, right? So then there's a question though. What if I had a different polynomial? What if I changed it so that it was x cubed minus 2x plus 6? So how does this factor into it? Well, let's see. Now, if you tell me that f of a should be a cubed minus 2a plus 6, that's terrible. That's a horrible thing even to write down, right? Makes no sense, because here we've got some square matrix, and so this is a matrix, and this over here, this is a number, and we can't add a matrix to a number. That's nonsense. Not defined. So we need to have sort of the matrix version of the number 1. And what I mean by that is we need to have a matrix that has the property that if you take A and you multiply it by this matrix, then it's like nothing happened. And since matrix multiplication is not commutative, we need to specify that it works like this no matter which side you multiply by. And so suppose we have the matrix 2, 1, negative 1, 3. And we want a matrix I that has the property, so it's going to have some, let's see, A, B, C, D entries. And it should have the property such that A times I is equal to A. Okay, well then this gives us a system of equations to that we can set up. So we've got A times I, and this is supposed to be equal to A again. So the equations that gives us, let's see, so we're going to have 2 times A plus 1 times C equals 2. So that's looking at the first row, first column gives us first row, first column. And similarly, we have, let's see, 2B plus 1D is going to give us 1, and minus A plus 3c is equal to minus 1, and minus b plus 3d is equal to 3. And if you solve these equations, you will find that the answer is a equals 1, b equals 0, c equals 0, d equals 1. And so this I that we're looking for is 1, 0, 0, 1. And this guy has a name. This is known as the identity matrix. And I suppose I should specify here that this is the 2 by 2 identity matrix, because of course you can have one for any dimension. So there's the 3 by 3 identity matrix and the 4 by 4 identity matrix, and so on and so forth. You have an identity matrix for whatever size collection of matrices or vectors you're working with. So now if we go back to f of x is x squared minus 2x plus 6. So let's think of this as x to the first power and x to the 0th power. And by convention, a to the 0th power, well, that's a 0, is the identity. Then that means that f of a is going to be a squared minus 2a plus 6 times the identity. And so now that we have that, we can totally go to town, and we can define all sorts of functions of matrices, because we can do things like take power series, right? So for example, e to the x, the power series for this guy, is x to the n over n factorial. And so we can talk about what e to the a is, for example. And it's the series of a to the n over n factorial. So even if the left-hand side, e to the a, looks really strange and weird, and it's hard sort of to imagine what it looks like, by looking at the right-hand side, you can see right away that this is some scalar multiple 1 over n factorial times some power of some power of a, and we saw earlier how to compute those. So this term right here is going to be some square matrix. Maybe it's like a k by k square matrix. And so every term in that series is going to be a square matrix of the same size, so we can add them all up. So apparently e to the a is some kind of a square matrix. It'll turn out later that this is actually a useful thing to do, but we won't come back to that until the very end of the course.